Manufacturing Research Center at National Cheng Kung University. And he's an IEEE Life Fellow and has served as the steering committee chair of the IEEE Case Conference. And he is internationally recognized for his pioneering work in intelligent manufacturing, Industry 4.0, and automatic virtual metrology. His research and technology transfers have made a strong impact on industries such as semiconductors, displays, and solar cells. And he has received numerous international awards and honors. Please welcome Professor Fan-Tien Cheng.
Okay, thank you for your introduction. So today, the topic that I would like to present is Industry 4.1, Intelligent Manufacturing with Zero Defects, and Industry 4.2, Green Intelligent Manufacturing for Net Zero. Okay, so Industry 4.0 defined the goal of digital transformation, aiming to enhance productivity. On the other hand, the core of Industry 4.1 is to realize intelligent manufacturing with zero defects, which is used to resolve production quality issue that receive relatively little attention in Industry 4.0, and it achieved the goal of not producing defective products. Further, developing the advanced technology of energy saving and carbon reduction based on the Industry 4.1 platform can assist various industries to realize not only digital transformation, but also taking energy conservation and carbon reduction into account. In this way, the goal of net zero carbon emission in 2050 can be accelerated for international competitiveness and sustainable development. This state is a so-called Industry 4.2, green intelligent manufacturing for net zero. So allow me to take the semiconductor bumping process as an example. So to begin with, we need to collect all the big data. So you see, this includes the final inspection data, then inline metrology data, and then the routing data, and finally, all the manufacturing process data. That is from the FDC. Okay, so let me use the semiconductor bumping process as an example. So after with the production line, the big data being prepared, then we need to install the IoT devices. I call it CPAs, to collect all the not only the process data, metrology data, and inspection data. After collecting all the big data, then we will transfer it into the cloud. Then we need to build a cloud here. This is based on the framework, the Advanced Manufacturing Cloud of Things framework. With this framework, then we can install various intelligent services, such as automatic virtual metrology, AVM, intelligent predictive maintenance, IPM, and intelligent yield management, IYM. So, and allow me to tell you the importance of product quality and the implementation of Industry 4.1. So let me use a video to show what is the importance of the Industry 4.1.
Professor Fan-Tien Cheng and team at the Institute of Manufacturing Information and Systems of NCKU established iMRC in early 2018 to align with Higher Education Sprout Project from the Ministry of Education. The mission of iMRC is to assist various manufacturing industries to realize the visions of Industry 4.1 and to achieve the goal of nearly zero defects of all products. Despite achieving the four core technologies of Industry 4.0, such as IoT, cloud computing, cyber physical systems, and finally big data analytics, I am able to use the AVM technology to make all manufactured product undergo total inspection, not just to care the health status of the equipment. What we need to care is whether the product itself is defective or not. If we can find out the defective product, we will reject them, Therefore, all deliverables are without defect. So the missions of iMRC is not only to exceed Industry 4.0, but also to achieve the goal of zero defects.
Okay, so then the importance of quality and the visions of Industry 4.1. So you see, Industry 4.0 emphasizes productivity, yet overlooks the importance of quality. And why? The key reason is the lack of an affordable and a practical online real-time total inspection system. So see, for example, Samsung Note 7 battery defects cause a loss of over 24 billion US dollars. And so you see, this because you see the customer, what they really care is what they purchase has no defect. If really there's defect in it, then they need to get it be fixed and need to exchange that. Then it's no good. And for example, for the automobile industry, okay, what they emphasize is zero defect manufacturing, etc. So in order to take care of this kind of zero defects issues, okay, so we need to have the zero defects production, and that is the vision of Industry 4.1. So in other words, it's important not to overlook product quality while pursuing productivity. So, and by integrating the intelligent service such as AVM, IPM, and IYM into the advanced manufacturing cloud of things platform, the goal of zero defects can be achieved. And this is the so-called Industry 4.1. Okay, so in fact, the concept of Industry 4.1 for zero defect manufacturing was published in RA data, IEEE RA data in 2016. Okay, so in order to implement Industry 4.1, then I need to develop the so-called intelligent factory automation system platform. So you see, in order to achieve the above mentioned goals, it's necessary to create this. This is a total solution for intelligent factories. So based on the advanced manufacturing cloud of things framework, our team has developed an intelligent factory automation, the IFA system platform. So see, this IFA system platform, in applying this IFA for Industry 4.1 to achieve zero defects, then the enabling device called the IoT. This is an IoT device called CPA. The CPA, okay, should have the functions of data correlation with the equipment drivers, which can which will have the interface communications such as OPC UA and SXGEM. And of course, it should have edge computing capability with the pluggable application modules. And of course, it has provide the functions of synchronizing with cloud services with this communication module. So with these CPAs, then we can connect the shop floor. Okay, the digital transformation, connect the shop floor and send it into the servers that install AVM, IPM, and IYM, and it will interface with the MES and ERP. So you see, this is the IFA platform. Okay, so if for Industry 4.0, then we will have cloud computing or cloud manufacturing services. Then you see in this version, the cloud-based IFA, you see, I just put these servers into the cloud. The difference is that, okay, so see, this is the concept, or this is the what I show to you, the IFA platform. Okay, so introduction to cloud-based IFA, and I'll use the video to show how the IFA operates. Okay.
By integrating technologies such as cyber physical agents, CPA, advanced manufacturing cloud of things, AMCOT, automatic virtual metrology, AVM, intelligent predictive maintenance, IPM, and intelligent yield management, IYM. iMRC developed the Intelligent Factory Automation, IFA system, as the core to upgrade Industry 4.0 to Industry 4.1 for realizing the goal of zero defects of all products. Now we'll start talking about the operation flow of the cloud-based IFA system. Let's take a semiconductor factory which is ready to implement IFA, for example. Here we can see the manufacturing process of it. It contains the process data of the equipment during production and metrology data during inspection. On the left, we have the existing MES system and the ERP system on the right. The block marked with background color is our IFA system. All the components contained in IFA will be described as follows. First, we have to install CPA. It will collect process data, metrology data, and other data from the ERP and MES systems and upload them onto the IoT application platform, which is supported by Chunghwa Telecom. As CPA is a significant part of the whole system framework, we'll talk more about it. CPA is a cyber physical integration agent component based on the technologies of Internet of Things, IoT. It is in charge of collecting the data of different machineries. CPA is equipped with different equipment drivers for various industries, such as SEX, GEM, and Interface A for the semiconductor industry, OPC UA, and MT Connect for machine tool industry, etc. Communication services for connecting internet and the cloud. Various intelligence services can be implemented as pluggable application modules and plugged into CPA for edge computing. Based on the IoT application platform, we construct our AMCOT, which includes big data analytics apps and manufacturing services automated construction scheme, IMSACs. Next, we'll explain the core intelligence services in the AMCOT framework. The first one is automatic virtual metrology, AVM. The main function of AVM is to convert offline sampling inspection with metrology delay into online and real-time total inspection of all the work pieces. This flowchart shows how the AVM operates in the IFA system. Take the lithography process as an example. First, CPA collects the process data, PAWS, from coder, stepper, and developer processing tools, and the corresponding sampled metrology data, effect, from the measuring tool as shown in the red square. Then, CPA does edge computing to execute data pre-processing and feature extraction. Next, all the key features are sent to the AVM server in the AMCOT platform. Finally, AVM can conduct processing quality inspection with these key features for online and real-time total inspection of all the work pieces. The next service we'll introduce is IPM. IPM can monitor the health status of a key device and predict its remaining useful life, RUL, of the device. With IPM, we can improve the tool availability and prevent unscheduled downtime. Take a device in the sputtering deposition tool, for example. The process data of the device are collected via CPA for data pre-processing and aging feature extraction of the key device. Then all the aging features are sent to the IPM server in the AMCOT platform. The IPM system then creates the RUL predictive model. After that, the RUL model is downloaded to the CPA. Finally, the CPA can conduct edge computing for RUL prediction of the key device. Let's move on to IYM. The IYM server can reduce the searching times of locating the key station, device, and parameter, which affect the yield from 8 to 24 hours to less than an hour, helping the engineers to quickly find the root causes that affect the yield and fit them. As such, and with continuous improvement, the goal of nearly zero defects of all products can be achieved. Here's how the IYM server operates. First, CPA collects the final inspection data in the defect report, production route data, manufacturing process data, and inline metrology data for data pre-processing and feature extraction. Then, the key features of all the data are sent to the IYM server in the AMCOT platform. Finally, the IYM server can search for the root causes of the defects efficiently. Besides these three services, there are also other intelligence services in the IFA system. The AMCOT platform is designed for pluggable applications. By the same token, we can deploy other intelligence services on demand with the same pattern.
So this shows how the IFA operates in the cloud-based system. Okay, so
By
see
integrating
now, and I use the key device is I should say the major intelligence services is AVM. Then I will explain AVM its function of AVM. So see the AVM, you see we need to collect all the process data and just a piece of the metrology data for this is only for training and tuning on a purpose only. Then you see the main purpose of the AVM is just convert the process data into the virtual metrology value, right? Then you see not only the VM values being produced, but also you see the AVM system generate the accompanying reliance index here of each VM1, the phase one VM value and phase 2 VM value. Users can check the reliability of the VM prediction via its corresponding RI value. Then promptness and accuracy can both be taken into consideration in the dual phase algorithm. Okay, so see this phase 1 is emphasize promptness, and then phase 2 improve the accuracy. So besides that, then we can take care of the data quality issues. So the AVM system can ensure the quality of process data and actual metrology data online and real time. Thus, the quality of the outputted VM values can be further assured. So this all been documented in I3 Project Transaction on Automated Science Engineering in 2012. So see, allow me to use this video to show you the AVM demo for critical dimension of photo process that was installed in ASE. Okay, that is a packaging company in Taiwan. Okay.
This video takes bumping process, for example. The virtual metrology Y is the CD value after the photo process. As such, lithography process data need to be added in to establish the cause and effect relationship for CD value prediction. The upper part displays the actual AVM conjecture scenario, while the black lines being the BPNN prediction values. The bottom part is the scheme of the bumping system. In a system diagram, when the lithography process data enter the cloud through the CPA collection, the AVM in the MCOT calculates new virtual metrology CD value in the cloud. As data keep entering MCOT for AVM conjecturing, delayed sampling inspection can be turned into real-time total inspection. After actual CD metrology, the values will be uploaded into the AVM of MCOT through CPA for model tuning to ensure the freshness and accuracy of the model. Finally, as shown in the Cheng chart, the actual CD value is 13.7623, while the virtual metrology value is 13.7963. With a slight difference of 0.034, it indicates great conjecture accuracy. Similarly, during the second actual sample inspection, Y data is uploaded into MCOT for model refreshing. The actual value is 13.8146, while the virtual metrology value is 13.8278. The difference is within the error tolerance, meaning excellent conjecture accuracy.
So then what is the benefits of implementing AVM? So as is after tool finish the processing, then we need to measure if we'd like to know the yield of that, and we need to measure the product. It takes about 1.5 hours. And that is the reason why only sampling inspection is conducted. You cannot measure all of them because it takes so much time. So to be after implementing the AVM, so the predicted metrology value is generated upon the production of each workpiece within less than 10 seconds. So with this kind of scenario, you see the benefits of that. You see not only the sampling inspection, not only those red one, but also you see those three, the green one, okay? It can have the virtual metrology value. So we can have 100% total inspection. And then we can lower the sampling rate. This can lower the sampling rate. And that it means less measuring machines and less human labor is in inspection. And the benefit beyond expectation is almost the zero waiting time. That is, we can reduce the queue time. Okay, so then the purpose of this is to integrate the function of AVM with those of the MES. Then why we need to integrate AVM into the MES? You see, the MES has a function of SPC, scheduling, order management, etc. But you see, in order to using the SPC to check the quality or the yield of the production, okay, then you need to feed in all the measurement data. But if you just give them the sampling inspection data, then it just can give you the sampling inspections SPC results. But if you really would like to have total inspections the result, then how we can do it? Then of course we can install AVM into the MES. You see the AVM will correct the process data and the metrology data and generate from the I should say the sampling inspection with metrology delay into real-time and online total inspection. So with this total inspections data, this AVM value not only can fit it into the SPC for total inspections SPC, but also the stage one, I should say phase one VM value can fit it back for run-to-run control, and the phase two VM value can feed forward for feed-forward run-to-run control. But not only the benefits of the supporting the wafer-to-wafer control and the total inspection SPC, but you see the AVM itself can check the reliance index and the data quality. So it will know is there any quality issues or equipment health issues or not. But you see, so if really there is an quality issue or manufacturing productions or equipment health issues, it will generate an alarm, and this alarm can be collected and be sent to the alarm manager. Actually, this result, actually I have already implement this AVM in UMC and ASE in Taiwan, and they like this function very, very much because their FDC functions doesn't have the capability of knowing the data quality issues or the equipment health issues. But our AVM not only give you the VM values, but also the alarm when the data quality is not good or the equipment process has some abnormality there, then he can generate alarm to the alarm manager. And you see, we still have connect this to a scheduler. Then I just mentioned to you that you see, it's about 10 years ago, I have a cooperation with UMC, and they asked me to convert that is the CVD process, and using the CVD process, okay? What they do is they have sampling inspection, that is 2 out of 25 samples. In other words, a FOUP has 25 pieces of wafers. They just have 2 wafers. But really, all the other 23 wafers value, then I can use AVM to predict that. Then they like it very much, but that is not their they just would like to have more functions. So they ask me, can I reduce the sampling rate? In other words, they ask me to reduce the sampling rate from 2 out of 25 into 1 out of 50. In other words, is reduce it to 1/4, only 25% of sampling time, sampling rate. So they told me, can I do it? I said yes, if your scheduler can be controlled by my AVM. Only when I ask you to have measurement, then you just doing the measurement. Otherwise, it's not necessary for you to do the measurement because our AVM, the accuracy is good enough. So they accept these options. Then after testing, yes, they really can convert, can reduce the sampling rate from 2 out of 25 into 1 out of 50. And you see, at that time, it's about 10 years ago. They have a phase to expand their production line. And at that time, originally, they would like to purchase 4 CT-SAM metrology equipment. And just because of our AVM technology, they just purchased 2 sets. In other words, they save 2 sets of CT-SAM equipment. Each CT-SAM equipment costs $400 million US. So you will see this is one of the benefits of AVM. And I would like to tell you that there is still other benefits. For example, for the etching process, you know that the etching equipment's process capability, or if you would like to know the etching process capability, you need to measure its etching rate. But the etching rate is not measured from the production wafer. It needs to be monitored by a monitored wafer for all control wafer. So in order to do so, then we need to save 3 or to 5% cycle time, and using the seasoning and using the control wafer or monitoring wafer to measure the etching rate. Okay, but with my AVM technology, I just can conjecture the etching rate from the production wafer. So with this case, then I don't need a control wafer at all. So I can save not only the cost of controlling wafer, but also save 3 to 5% cycle time. And just because this 3 to 5% cycle time originally is for seasoning, now those 3 to 5% cycle time can be used for production. In other words, the productivity can be increased 3 to 5%. That is significant. So you see that is the benefits of AVM. Okay, so next one. So the main features and the benefits of IFA. The IFA can accomplish big data collection infrastructure for intelligent manufacturing. That is using the CPA, the Internet of Things and Edge Computing. Then we can accomplish in cloud computing platform using the AMCOT platform with the technology of cloud manufacturing. Then establish information security monitoring system with IoT information security monitoring system. Okay, then improving the utilization rate of the factory and monitoring the overall equipment effectiveness, OEE, with EMS. And of course, we need to accomplish the total quality inspection on all workpieces with AVM. So, and then improving availability of production tools with IPM so that the remaining useful life RUL prediction can be achieved to avoid unscheduled down. Then we can constructing the root cause identification infrastructure for year loss with IYM so that the root cause identification of year loss for continuous improvement. So all of the benefits and the features can convert into achieving the zero defects of all products for Industry 4.1. So the strategy to achieve Industry 4.1. So we see the phase one, what we will consider the all deliverables first. So you see, and then it's very straightforward. If you would like to guarantee that there are no defects in the deliverables, then how we can do it? Of course, you just use total inspection. Not only the work in process WIP or the final product, final deliverables. You just use, you see, I have the technology of AVM and using the AVM to do the total inspection. So after inspection, if there is a defect in it, then of course just discard it. And after this AVM total inspection, if there are no defects, then you after deliver all these product to the customer, they will be happy because it's no defect at all. So that is the first phase one. But you see, if the yield is only 80%, then in other words, there are 20% product has defect in it. Then the manufacturer would like to improve the yield. In other words, those 20%, it's better to find out the root cause of those 20% and then try to have continuous improvement. And then how can we do it? The purpose of that is try to achieve the goal of zero defects of all the products. Of course, this is by big data analytics and continuous improvement. Then how can we do it? Just by IYM, I just mentioned to you already, right? In intelligent yield management, it can find the root causes of the yield and improve it. And of course, another technology called advanced process control or wafer-to-wafer, run-to-run control. Okay, so you see, if, for example, the CPK, or if we find out that the target value, in other words, the product cannot, it's already may go to, may exceed the threshold. So before it really exceed the threshold, we will use the APC technology or run-to-run technology to bring it back. So this is one of the approaches to prevent the defects. So you see, by using these kind of approaches, we can assure that all the products we are approaching nearly zero defects. Okay, so various application scenarios. And what are the various application scenarios? I have already implemented the IFA in semiconductor industry, for example, in ASE, to achieve the goal of Industry 4.1. And then the automobile industry, the Fabcom, and blow molding industry, Chain Power, and the carbon fiber industry, that is Formosa Plastic. This is door-to-door process, then I still can implement AVM on it. And then the aerospace industry, the AIDC, and then the paper industry, the CHP, and the chemical industry, HOPEX. Actually, this is only the typical one. More examples are still being implemented in various various industries. So my research team integrated all the core technologies of the innovative IFA systems platform and the various intelligent application modules such as AVM, IPM, IYM, etc. that has been developed successfully over the years, along with practical application cases into an English textbook entitled Intelligent, I should say Industry 4.1 Intelligent Manufacturing with Zero Defects is this one. You see, and you see the cover is the IFA pictures. Okay, so this book was published by Wiley IEEE Press, okay, and released on October 2021. And then the Chinese version was released on January 2023. So both are in hardcover and ebook versions. Okay. So now I switched the gear from Industry 4.1 to Industry 4.2. So evolution from Industry 4.0 to 4.1 and to 4.2. So Industry 4.0, the main is to achieve digital transformation and enhancing productivity by implementing the CPA, the IoT devices here. So the Industry 4.1 is trying to accomplish in zero defect manufacturing by AVM, IPM, IYM. This was documented in the textbook I just showed you. Okay. Then we have moving was one step further to Industry 4.2 to fulfilling net zero manufacturing by aiding intelligent energy management and intelligent carbon management. And this actually is IEEE TSE journal papers just published 2 or 3 months ago. Okay, so you see, now allow me to present the green intelligent manufacturing for Industry 4.2 to achieve net zero. So see, if in order to achieve net zero, not only the factory production line, but also the facilities, factory facility systems need to be taken care of. So the same, I will develop an Industry 4.2 framework. Okay, this is the framework. Okay, and the whole system will connect it in to those production line and facilities. So you see, this Industry 4.2 framework, including the ICT platform, information and communication platform. So this including the blockchain, security protection, and the containerization. Okay, and then of course, not only consider the energy management and carbon management, but also you see the original zero defect manufacturing technology, the AVM, IYM, IPM in Industry 4.1, of course, still can be reserved here. Okay, so you see, then we will develop the intelligent carbon management system and the intelligent energy management system. And of course, we can also implement the intelligent virtual power plant and the blockchain I just mentioned about it. And that is for carbon and energy trading. Okay. So the basic requirements and workflow for realizing Industry 4.2. So you see, the first step, of course, the same is using the CPAs to have to collect the big data. That is the big data collections. Then you see those 3 blue blocks of step 2, 5, and 6 try to perform the core function of energy management. And then the 3 green blocks of step 3, 4, and 10 performs the core function of carbon management. And then step 5.5 and 6 is perform manufacturing operations. And the yellow portion and will continuously conduct process control among those blue, green, and orange blocks via decisions. And the purpose of that is try to check is it reach the goal of net zero or not. So you see, then we will use the blockchain to consider and for further carbon and energy trading. So see, so the detailed relationship between the energy management and the carbon management. So you see the stage 1 here, the production scheduling is try to optimize cost of hardiness, production, and electricity, and the carbon emission. Okay, and then the stage 2 is for facility parameter control, try to optimize cost of electricity and the carbon emission. Then stage 3, that is for micro grid allocation here. So optimize the cost of electricity equipment operation, charge discharge efficiency, and fuel and carbon emissions. And then the carbon management is try to determine how much energy can be used or has to be used for carbon reduction and energy distribution. And please pay attention to here. You see the main key functions here is I call it the third version. I should say third generation of AVM, automatic virtual metrology, shown here. This is what's used to predict the energy to the baseline, to forecast the energy baseline. So you see, we need to have the energy baseline forecasting so that the energy saving and carbon reduction can be achieved more efficiently. So allow me to show you what is AVM3. So you see the intelligent management, intelligent energy management, the core technology is energy forecasting. So energy forecasting is the foundation of all energy management activities. So you see, to begin with, of course, we need to collect all the big data from the production information, facility information, environment information, and the power meters, etc. Then after collecting that, we need to check the quality of those data. And then you see, we need to find the optimum memory length P, forecast length F, and a full cycle thread length T. And then using the transformer model and the LSTM model to predict the energy baseline. So you see, using the LSTM and the transformer to do so. And you see, this is the third generation AVM. So not only the prediction value, but also the reliance index are still in here, and we can check the data quality there. So you see, with this AVM3, you see, we can predict the energy. We can forecast the energy, but you see here, the predicted accuracy is no good. So then we will automatically ask it to refresh or retrain the model. And after retraining, then you see the tracking accuracy coming back. So we do have the capability to do energy baseline forecasting. Okay, and with this technology, so you see, we can include it in here. So using the energy baseline forecasting, then using this predicted electricity load and combine with the product information to do production line scheduling, so that we can we can save the energy by this kind of scheduling, so that we can distribute the power more efficiently. And not only in the production line scheduling, but also in the intelligent facility. You see, the AVM3 energy baseline estimation is put in here. So see, this is the key functions. So with this predicted electricity load, so that intelligent facility management can be achieved more efficiently. Okay, so see, this diagram show, you see, the red line is the power consumption before optimization. In other words, if without the AVM3 or without Industry 4.2 adjustment, then that is the original, that is RCs. And the blue line is the forecasting, energy baseline forecasting by AVM3. Then based on that energy forecasting, then we can redistribute or tune the system so that the power will be reduced. So in this show, this one is the chiller's temperature. The red one is the without the Industry 4.2's adjustment. But if with that one, you see the temperature can be tuned. There, this is the temperature of the chiller, and this is the pressure of the compressor. So you see the compressor previously just about stick in 5.2, but with our adjustment, AVM3 and the Industry 4.2's adjustment, then it can tune it down, but still maintain the production quality, etc. But you see, with this kind of technology, we can have more efficient energy reduction and the carbon reduction. Okay, energy conservation and carbon reduction. Okay, then the next one. Okay, so this shows the intelligent virtual power plant. You see, in each company, we can implement Industry 4.2 to achieve nearly net zero. But you see, we still can use the microgrid to consider the solar energy and energy storage in the Industry 4.2, right? But you see, an enterprise, they may have several companies, several factory sites. For example, in Taiwan, they have Formosa industry, they have 4 sites. And then you see each site can not only implement the Industry 4.2, but also the virtual power plant. And this, we can use the blockchain to connect them with one another. And they can trade the energy with one another. If they have more energy, they can sell it back to the Thai power, etc. So this is the concept of Industry 4.2. Thanks.